Is Anand Venugopal, or AV, from Impetus Technologies. We're one of the sponsors here in this conference. We're a big data solutions integrator that's doing a lot of work around Cassandra and Hadoop. And one of our early white papers in 2009 on Hadoop configuration actually attracted the attention of our pioneer Rich over here. And it's my pleasure to introduce Rich. Rich Hamill is the Director of Advanced Manufacturing at Brocade. And he's worked in product development for about 18 years, from HP, Agilent, and now in Brocade. And Rich stuck his head out from the manufacturing world and got a peek into big data and then pulled Brocade into big data to deliver competitive advantage in manufacturing, and he's going to tell you the story. So, pleasure to introduce Rich. Rich, over to you.
Thanks, Anand. And so first of all, I'd like to thank DataStax. This conference has been tremendous. I've learned a lot of things here, actionable things that I can bring back to my company. So I do want to thank them. Tremendous venue. Walking from these different talks from one building to the other with this view. I actually live in San Francisco, and seeing all these sites is just breathtaking over and over again. So do want to thank them. I also appreciate the opportunity to talk to you about something that I'm very passionate about. So that's fantastic too. I'd like to start off by saying that I am not in IT. I'm an engineer. I think the last programming language I took was Fortran, so I think that dates me a little bit. But I do want to thank you guys. A lot of people in the audience here have developed technologies and tools that can be used across all kinds of industries. And these tools I can see already, they're going to help me do my job a lot easier. But more importantly, they're going to allow me to do things that I couldn't do before. So I do thank you for that. So with that, what is it that I do? And let's see here. Okay, so this is not working, so let's see if we can do this. Okay. So here's a list of Brocade products that we work on. When I started at Brocade in 2003, it was just the blue circles there. At the time, we were just a fiber channel company working on storage networks. And basically, we had one product line with 3 products in it. The one in the center is what we call a director. It's a chassis-based product where a number of blades go inserted into that chassis. And then we also had a few pizza boxes, which are 1U devices. Looks kind of like a VCR or a piece of audio equipment. Goes into top of rack applications. So that's where I started at Brocade. Since then, we've expanded our portfolio quite a bit. We now develop embedded switches that go into servers from some of our OEMs, IBM, Dell, HP. All of those companies have embedded switches that go into their servers. So that was our first foray into kind of expanding our product portfolio. Then kind of the big thing that changed this was in around 2008 timeframe, we bought a company called Foundry Networks that was into the Ethernet space, LAN products. And from them, all the rest of these products came on board. And I'll talk a little bit about some of the problems we saw when we did that. But you can see up here on the top left some of the lower complexity, lower cost products for the campus enterprise. There's wireless, there's pizza box products. In the center here, we have some of the more complex products for service providers and data centers. So these could be anything from a closet-sized chassis, and again, going into some of the internet exchanges and some of the bigger data centers in our customer base. So one of the other things I want to mention that did not make this slide, but that is actually over to the right, is some of our new products, some of our Ethernet fabrics. And those things are very, very interesting, brand new technology. They're self-healing fabrics that scale to big data applications. So very, very new product. I'm hoping in the next year or two that when we come to conferences like this, more and more people will be talking about using these types of products in their installations. So let's see, that's it on products. So a little bit about manufacturing, and I know it's not the most sexy topic to be talking about here, but manufacturing is big. There's a lot of things going on right now. For those of you that followed the presidential election, a lot of talk about manufacturing jobs and what it takes to bring those jobs back to the United States. Let's see. So with that, I think there's a huge opportunity. I think actually some of the tools that you guys are developing can be used to gain us significant advantage in manufacturing. And I'll talk a little bit more about that in a second. You'll see some examples of that. I don't know if you knew this, but manufacturing, 90% of the patents that are generated in the U.S. are related to manufacturing. 70% of the private R&D in the U.S. is related to manufacturing. And 50% of the exports from the United States are related to manufacturing. So manufacturing is still big. Just electronic manufacturing alone. So if you look at cell phones, you look at computers, you look at some of the things we're doing on the network, the servers. If you look at all of that, in 2013, that market is expected to be about $1.3 trillion. So, anything we can do to help out this industry, they have a lot of money. So that presents opportunity. Let's see. A few other things. Time to market is shrinking. Things are getting a lot more competitive, especially in the networking space. So we got in pretty early, but after that, Cisco started focusing. They were buying video, they were doing all this other stuff. But after that, they realized they really needed to focus on their core networking space. So they're focused there. They're a big company, but they're focused. In addition, companies like HP, IBM, and Dell separately bought networking companies. So a lot of people, and then there's, of course, Huawei in China. So there are a lot of companies that are focusing in this marketplace. So time to market is a key differentiator. And we, at Brocade, feel like we have an advantage there. Cisco's gigantic. We're a much smaller company. We can react a lot quicker than they can. So I think we have an advantage there. And I actually showed a graph here. It's really nice to see this. It was interesting looking at our time to market over time at Brocade. So this is from the time of concept, and I didn't give any y-axis here for the people told me no, you can't divulge that, but at least it shows scale. And it started in 2001 with our first fiber channel products, and you can see a really nice decline in that time to market during that time frame. And then you can see that little lump up. That's when we bought Foundry. So we took a hit there, but then you can see the same trends going down. So we're very, very focused on decreasing that time to market because we feel it gives us considerable competitive advantage. Another thing that's going on, teams are much more distributed. We have contract manufacturers. We have development teams in China, in India, in the U.S., all over the world. And we need to be able to collaborate on this data, both within our company, across geographic boundaries, as well as across other companies. So that's another one. And then finally, just in general, data is more important. I don't know how many of you follow the news, but the president recently designated $1 billion to invest into his concept of smart factories, which means all of the information, all of the tools in a factory are all integrated together, and we collect that, looking at common ways to collect that data, store that data, and analyze that data. Once again, for competitive advantage for the U.S., specifically around manufacturing. So a lot of stuff's going on in manufacturing. So I briefly wanted to talk a little bit about our manufacturing process. We make printed circuit boards. An example is down on the right-hand side. I wanted to show some pictures of what these factories look like. It's quite interesting. You look down the line, and you can see machine after machine after machine. So all these machines generate data, and that data we can take advantage of. So quickly take you through the manufacturing process. I'm not going to stop at every single stage, but I wanted to give you the gist of it. So we start off with a bare printed circuit board. It's the green thing that you see inside of a computer or inside of a server. At that point, there's a paste printing process. So solder paste starts off and it's screen printed, much like a T-shirt is screen printed. You screen print that solder paste onto the board, place components onto that, and then reflow it. Basically heat it up, melt that solder so we get a nice, clean, solid solder joint. At that point, it's inspected. We do X-ray inspection to look for voids. We also do in-circuit test. It's basically a bed of nails test that comes down and tests all the different components on a board. In some cases, we have up to 50 or 60,000 components on one board. So we really need to understand whether some of those components are bad or not. That would be the first place we do that. And again, I'm skipping over some of these, but and then at the very end, we have what we call functional tests. We start off with board functional test, which is a benchtop room temperature test. After that, we perform stress testing. We put it in a chamber, big ovens. We cycle temperature. We run it constantly at 45C. We voltage margins up and down. We power cycle the heck out of it. We run traffic on all ports at the same time. So we're really trying to hit these things hard in the factory so that our customers don't see the kind of failures we would see early on. So again, a picture of the finished product is down here. This is a Brocade encryption switch. And you can see on the left-hand side, that's where all the SFPs or the RJ45s, in this case SFPs, are plugged in. In the center, the gray boxes, those are all the different pieces of silicon we use. And then on the right-hand side, the connectors to the backplane. So this goes into a big chassis. Okay, let's see. So a little bit about statistical variation, and this is very, very important, especially with complex supply chains. So I shrunk it down, what I just showed you here, and I showed a printed circuit board kind of in line with that, and the variation that's associated with that printed circuit board. As all those different machines that we're using to build our products, as they vary over time, you get statistical variation at each process. And so consequently, you get boards out of that process that have variations in it. And when we do that, when we install those boards into a system, the same thing happens. We get statistical variation around that system. Now, it gets more complicated than that. If you look at remember the complex supply chain we're talking. So we have components that go into those boards. They have their own processes. They have their own statistical variation. Build that out even further. We have material suppliers to those components. They have their processes. They have their statistical variations. So you can see when all this statistical variation adds up, we get this graph down in the center. So we have this nice bell curve for the good material. And then we get all these little defective subpopulations of product. As you can imagine, if these things are not lining up appropriately, you get stuff out to the left here that is really not suitable to build a long-term reliable product. And so basically, what do we need to protect our customer from all this? We need end-to-end traceability. We need to be able to trace material from all the way up top, through components, through boards, through systems, back all the way to our customers. So if we see a problem with a material, we should be able to know what customers have those products. Finally, after that end-to-end traceability, we also need quick identification of non-conforming material. The faster we can identify this, the better chance we have of preventing it, of getting to our customer. Okay, so all this statistical variation, as you've seen already, represents risk. Risk to us, risk to our suppliers or our customers. I showed this slide that I showed on the previous slide. I want to spend a little bit of time on this graph. This is a standard reliability graph that we use to assess failures, when failures are happening. The x-axis is time, and the y-axis is failure rate. So normally, during the course of a product, you're sitting here at a useful life with a standard failure rate. But what happens is early on, you get what we call infant mortality failures. These are defects that are introduced in manufacturing. Those fail a lot faster, and they fail a lot more. So I have this up to 4x the failure rate of the kind of the steady state failure rate. So these are the ones we're focusing on, these infant mortality failures. And then you see that useful life, and towards the end you start getting wear out. Things age, things change a little bit, and you start getting failures. So again, our goal is to prevent these from getting in our customer hands. Provided some examples of some of these infant mortalities, which are very, very interesting. And these are real problems that we saw both at Brocade and some of my previous lives at other companies. So I'll take you through each one of these. The first one was titanium contamination. This was a voltage regulator that we had on a board, and that supplier received defective material from their supplier with titanium in it. And basically what happened is that titanium presented itself inside the part, and these parts were failing in our factory. Didn't fail at our supplier's outgoing test. It failed in our factory. Luckily, these were failures that we caught fairly quickly, so no risk to our supplier, contained in the factory. That's good. Next one, printed circuit board barrel cracking. So printed circuit board, the green thing that goes inside your servers and such, that actually has a very, very complicated manufacturing process. And in this case, what happened was one of our suppliers did not bake this part long enough before going to their next step. So there was a little bit of water vapor that was resident in the laminate of this material. So what happened was, when we got this material and we ran it through our reflow profile as we're soldering the parts onto the board, that water vapor expanded, and especially boards are susceptible to expansion in the z-axis, and what it did is it cracked these barrels, these copper barrels. This one was a little bit tougher. This one failed later on in our process. We still contained it in the factory, but it still was an issue. And then this last one is very, very interesting. I mentioned the time to market considerations we have. Well, in this case, a lot of times, in order to achieve that time to market, we co-develop products with some of our suppliers. So in this case, we were designing a brand new router. At the same time, one of our suppliers was designing one of their components to go in that router. So you can imagine all the balls in the air. When they're doing development, we're doing development, all the things that could go wrong. And in this case, something did go wrong. The outgoing test process at our supplier, basically they forgot to initialize one of the power supplies. And in some certain conditions, that power supply applied -7 volts to these devices. And what that did is it cooked the device, but I guess it didn't fully cook it. It was just a braise, I guess. And what that did was it created these pinhole defects in the polysilicon. And this one was a real tough one. Our first failure on this was 30 hours into a 48-hour test. And unfortunately, by the time we root caused this, we had shipped some out to our customer. So what did we do? We did analysis to figure out how many of these would fail after year one. And we actually proactively went to our customers and said, look, you're not having failures right now, but we feel that these components here will fail at a rate that's not acceptable to you. There were some suppliers that said we want to swap out the gear, and we were fine with that. There were other suppliers that said, no, we're not worried about it, we're fine, but we really appreciate you telling us that. So, and I think in both cases, they both appreciate us going to them proactively and saying, look, we think you're going to see some failures. So, this kind of runs the whole gamut of material type issues, component type issues, and then kind of parallel develop stuff. Okay, and so what can we do to prevent these types of failures from happening? Test hard, examine every failure, and speed of that analysis matters. So we need to be able to identify root cause, contain it in the factory before the stuff gets shipped out to the field. Okay, on the importance of test, at Brocade, we test the heck of our products. We really do, and we spend a lot of time doing that, and I think we want to prevent our customers from seeing these types of failures. I actually remember being at one of our contract manufacturers one time, and it was my product. I was bringing it to market, and it had passed a test process, and I said, let's test it again. And the guy was like, no, we're not going to do it. No, you're crazy. Don't do it. It's going to fail. And I was like, I want it to fail. That's the goal, to try and make things fail so we understand those failure mechanisms. So we really push hard in that area. One of the things about that testing is it generates a lot of log data, and we need to analyze that log data. So one of the best ways to do that is time series evaluation. There's a lot of time aspects of this analysis that are important. And I gave some examples here. This is actually a real-world project a real product that we worked on, and this shows some of that stress testing. You can see the temperature going from -10 to 60. So it's actually stressing solder joints. It's stressing performance quite well. And the red triangles there show where things were failing. 90 to 95% of our failures are intermittent. They happen under certain corner cases. And this type of visualization really helps us understand the conditions under which things fail. If it's only failing at hot, that gives us an idea on how to do root cause analysis. So that's one aspect of it. The other one down below, this is a standard Weibull plot that reliability engineers use. And they use it to, so for example, on that, on the one I showed you with the pinhole defects, it failed at 30 hours at a 40-hour test. We can then take that time to failure, put it into this Weibull plot with an acceleration model, and figure out how many are going to fail in the field. So this would actually help us determine whether we need to do a field action or not. So it's pretty important being able to analyze the time series of this data to help us execute our business processes. So I want to talk a little bit about how these files, all these log files that we're talking about with all this rich information is brought back, to our systems for analysis. And this system was designed around 2006 when we had one product. It was very, very easy. We had one software train, so it was very easy to control the output of those formats. We have worldwide manufacturing sites in Asia and America and EMEA. Those files are stored on servers at each one of the manufacturing locations. It's rsync back once a day to our data center. And then we have this parser that we developed, that's written in Python. And it uses an interface spec. So what I did is I went to the software teams and I say, look, I need something to key off of to parse this data out of your files. And we ended up with hashtags. We have things like ERR pound to designate an error, and a few other things there. So we defined this spec. It was great with one software team, very, very easy to do. So that would convert the raw log files into XML, which would then get updated into our data warehouse for analysis. So this was the good days. This was before we bought Foundry. This was all SAN. Everything was unique. Everything was consistent, and life was good. So what happened? 2006, we had one. This is a few years after Foundry. We had 7 product lines then, and 7 different OS teams. So trying to maintain that interface spec around 7 teams was very, very difficult. In addition, you saw, I know it's funny, the development teams always say, you don't have big data, you don't have big data. But I would argue that the data we have is complex enough to use some of the big data tools. So let's see, so when that happened, these were the consequences. So first of all, our parser broke. We didn't have all the hashtags available anymore. Because of the size of the data, the rsync processes took forever. Some of the other downstream processes also took for a very long time. In addition, we had to buy new NAS servers to store all the new data that we had. And because that parser broke, what we started doing is each individual user would sync files from here and develop their own scripts to parse them. So you can see, this is a mess. We have some files going in one direction, some files going in another. So how are we going to solve this problem? So this is where this project started. So we have store, we have parse, and report. We divided into 3 groups. I won't go too much into detail about the project. Parser would serve as a repository of errors. It has alerts for new errors, which is really good. If it finds an error that it's never seen before, it'd give us an alert. We can parse and analyze 6 gig in less than a minute. Storage, scalable because of the files we're looking at. Rapid access to files and full search capability. Reporting, I won't go to that into detail. The system needs low latency, flexibility, and monitoring. So you can see the approaches we use: Java and Storm, Cassandra and Solar, and then we're still actually deciding on the reporting side. Timeline, real quick, we started our consulting engagement with Impetus in October. It looks like about a year project, October 12 through October 13. We developed a proof of concept parser and a reference architecture, functional spec, and then we expect parser and storage to be online in August, reporting in October. So we're still in the middle of the process. I think we're going to have our first version of that parser next week. So let's see. I did want to talk about this because we're preparing our organization to take all these tools. So one of the things we did is establish metrics up front. We have this aggregate yield metric that rolls out. This is used to establish bonuses in our company. And it rolls all the way up to executive management, all the way down to the individual contributor. So it's a pretty powerful metric that gets everyone aligned on what we're doing. We also establish processes to support those metrics. So this is an example of yield metric. I won't go into this because I think I'm running a little bit out of time. So if anyone has any questions on this, they can ask me later. This is the concept of the parser, a flexible parsing engine with adapters for each types of log files. Those adapters define configuration, environmental information, time, temperature, etc., specific tests that are run, and error information. A little bit about ROI. I want to talk about that briefly. I spend a lot of time talking to my team. How are you spending your time? What are you doing? The green represents the stuff that we're talking about here. We estimate by automating that, we can get 10 to 20% efficiency gains per person. We can also contain more non-conforming material in the factory. So that's kind of the hard ROI. The soft, collaboration between teams, both in the factory. We get log files from the field, too. So we need to be able to collaborate or correlate that data. We also get data out of development. So if we can actually have a holistic view of everything that's happening in all those locations, that's great. Let's see, I won't go in the rest of that detail. Other possibilities that exist. We have, as I mentioned, here are all the machines we use to manufacture our product. Those all generate images and log files. If we can capture all of those, then we have a much more holistic view of what's happening in the manufacturing arena. And then finally, keys to success. I wanted to include a few of these. Technology is easy. All right, but people are hard. It's really easy in technology. We have equations, we have other things, but people don't necessarily have equations. So that's the tough part. So relationships are important. I heard someone say, bring the IT team out for drinks. I'm from New Orleans. Food's important to me. So we all went to dinner that night. We found out about each other's families. We found out about our kids, everything else. Those relationships are very, very important to when issues happen, you can fall back on those relationships, and it's not that big of a deal. Metrics and processes I already talked about, clear R&Rs, but one of the key successes on our team is we had people that can straddle both areas. Our last con call, development teams were asking me questions about my business, and our IT team was answering all my questions. So that's a key success sign for a highly functioning team. Context and not just content, And then this last one is big. Look hard for win-win opportunities. There are other organizations that need different things on a project like this. It may mean more risk for me to develop this project, but it gives the other organizations the information they need to make this thing successful. So that's another big one. Okay, so that's it for me. So you want to get up in here and talk? So Vivek's going to one or two more slides on Impetus.
Thanks, Rich, and as Rich mentioned, they started the consulting engagement with Impetus about 9 months ago, and we were able to push this project through. It's almost near production. I'm not going to spend a lot of time on the architecture. I'm just going to basically, this is a fantastic use case of real-time analytics on machine data. And those of you who are interested, feel free to come talk to me later. So it uses Storm, Cassandra, as well as Solar. And this is sort of the high-level overview. Don't worry, I think the slides are going to be available later on. And we actually did a detailed technology comparison, so it wasn't that we just picked Cassandra out of the blue. Several competing technologies were evaluated, and Cassandra came out on top because of several reasons, some of which you can see out here. This is about Impetus. So we were one of the early drivers for big data adoption. We are a big data SI and a consulting company offering analytics solutions as well as big data platforms. So if you have any more questions, we should be available. Please feel free to get in touch with us. Thanks.